In this video, I'll be explaining how we managed to edge out up to half a frame of average rollback length over traditional rollback for SSBM netplay by using a netcode enhancement which I call Subframe rollback. But before getting into this, we should first refresh our memory on netcodes. This is a timeline. Fighting game engines are typically incremental. That is to say that at a fixed frequency, usually 60 times per second, they will construct the next game state, which we call a frame. To do so, they will use controller inputs. Here, I've represented the game engine using the current inputs. In reality, that's not really possible, and these arrows shouldn't be vertical, because input lags the thing. But let's pretend it's not. These inputs come in the form of controller states. This is the real evolution of whether B is pressed. The only thing the game engine is told about is that at this frame, B is currently pressed, and at this frame, it wasn't. Since it used not to be pressed, and now it is, that's a B input, and Fox will shine. Now, let's say we're playing online. When our opponent inputs something, this information will take some amount of time to reach us. Let's say it takes 30 milliseconds. This means that the ping is 60 milliseconds, since ping is the time for a back and forth. Since information takes 30 milliseconds to travel, which is 1.8 frame lengths, if they send information on n-2, we will only receive it shortly before we have to build frame n. So here, the basic solution to handle transmission time is to always use inputs old enough that we'll have the time to receive the inputs before needing them. For example, we could decide that we'll always use inputs that are 2 frame lengths old. This amount of time is called the delay. So, the B input that would normally be used for frame n-2 will instead be used for frame n, and Fox will shine then. Of course, sending our n-2 inputs for them to use on frame n means that locally we'll be using these inputs for frame n as well. For the record, in Melee's case, the average good PC setup emulates Melee 2 frame lengths faster than console. So the standard online delay is 2 frame lengths, and these even out to match console visual input latency. So, by picking a delay, you establish somewhat of a contract. As long as the inputs arrive in time, everything works great. But if they don't, then you have a problem. Let's say that suddenly, the connection temporarily gets worse, and now we need 40 milliseconds to communicate. So, at this point, we are supposed to be frame n, but we don't have the inputs. They will arrive shortly, but we need them now. So, what do we do? Well, this is where netcodes matter. The simplest solution is to say, I don't know how to deal with this, freeze everything, we'll resume when we have the input. Which looks something like this. Frame n-1 got extended until we had the input for frame n. Since the same thing must have happened to them, they must have frozen too, and this scenario will repeat over and over. This is how FPSs drop as a consequence of ping spikes, which feels awful. You can try to mitigate this. For example, you could try to dynamically adjust delay to ping. But then this brings other problems, because players are conditioned to expect a certain amount of input lag, so changing it messes their timings up. And if such a delay adjustment were to occur in the middle of a combo, the timings of your inputs relatively to one another would get distorted. So, while this solution is simple, it leaves much to be desired. A better way to handle this is to acknowledge that you don't know what their inputs are at this point, but you're going to proceed anyway. You're going to make an assumption on what their inputs are, simulate what the game would look like in this case, and present that to the player. And by assumption, I mean assuming that nothing has changed since the last controller state we knew of. Which is usually correct, or in the case of games with analog inputs, usually almost correct. So, what this would mean here is that since at frame n we don't have the inputs, and on the previous frame B wasn't pressed, we mistakenly assume B wasn't pressed at frame n either. So this is what we see at frame n. We see Fox standing there, which is wrong, Fox shined. And so, the next time the engine runs, if we received an input for a frame for which we didn't have them, we'll compare the real inputs to our assumption. If it was correct, that's good, we'll pretend nothing ever happened. If they're not, like it's the case here, we're going to load the earliest game state before we diverge from the truth and reenact the game all the way to the present, taking into account the newly acquired information. In this example, it means that when we're about to build frame n+1, we realize that we have new information for frame n and it differs from our assumption. So we go back to the game state at frame n-1 and recompute frame n taking into account the B input we've just learned about, which makes Fox shine. and then compute frame n+1. The result is that at frame n+1, we are shown the second frame of Oxy Shine animation. We say that games that handle missing inputs this way have rollback netcode, whereas games that freeze on missing inputs have delay-based netcode. For the record, I don't like that name very much, because you can see that rollback netcodes can use delay too. What changes is what happens when the inputs don't arrive in time, in which case it rollbacks instead of freezing. So I feel that delay-only netcode or freeze netcode would be more accurate names than delay-based netcode. But it is what it is. So let's go back to our rollback example and say that we are actually playing at 40 millisecond transmission time all along. So every new frame will roll back one frame. Well, there's something a little saddening with this scenario, and the fact that I bother to represent the real evolution of the B button may hint at what I'm talking about, which is that it would have been physically possible for us to know about the B press in time. Putting aside all software architecture considerations, they knew that B was pressed at this point. And the time between that and us needing to know about the B press is less than the information transmission time, which in our example is 40 milliseconds. So we're going to be mistaken at frame n, only because the information that B was pressed in between these frames is only sent at this point. It's only sent when the game engine runs, because they only send inputs that are the definitive ones for some frame. But if, as soon as they learn about the B press, they were to send the current controller state along with a tag that says, I am the controller state for this point in time, so n-0.8, we would receive that message at n-0.4, before we have to build frame n. And when we get there, instead of using the pad data for frame n-1 as usual, we would notice that we have more up-to-date pad data, which incorporates some changes that occurred between frame n-1 and frame n, and will therefore be present in the definitive pad data for frame n. So we're going to use that, because the more recent data we use, the more accurate a prediction of the frame n pad data it is. And in this example, that means that at frame n, we know about the B press, and we'll get to see the shine as it happens. And then, on the frame after that, when we'll have acquired the definitive input for frame n, if there's anything new since our prediction, which is based on the content of n-0.8, we'll still roll back to the definitive input, but we'll be rolling back less than a frame length's worth of information. In fact, when it comes to major changes in controller states, since anything important that would have happened before this point would have also triggered a message that would have arrived in time, we'll only be rolling back by this amount of controller state evolution. And in our example, that's 0.4 frame lengths, because it's transmission time minus delay, and here these are respectively 2.4 frame lengths and 2 frame lengths. And that's the core idea of the Subframe rollback enhancement, which I named after the fact that it enables rolling back by a fractional number of frame lengths worth of controller state evolution. We're going to add a stream of input messages alongside the existing one that handles definitive inputs that will be triggered by the perception by the emulator that the controller state changed in a way that is important enough that it warrants sending an update. So then, what is important enough? Well, this question only really makes sense because Smash uses analog inputs. The gamecube controller has 2 analog sticks and 2 analog triggers, and provided they use an adapter and overclock the USB polling rate, you can have 1000 controller states per second coming in, with ever so slightly different analog values. Of course, you're not going to send 1000 messages per second, because your network would die. So that means that we have to make a judgment call about which analog changes deserve to trigger sending an update. It's about network cost versus prediction accuracy benefits. Like, if I jump and slightly adjust my airborne drift, it will take multiple frames for a difference to even be visible. Or if I slightly adjust my shield size or angling, then it's not crucial information either. It's not sensitive down to the frame, like the fact that I shielded in the first place would be. And that's because shielding, aside from having a clear frame 1 tell, greatly matters gameplay-wise. Shielding means that now I can only do out-of-shield options, like rolling or jumping, and that's important information for the other player. And it's the same thing if I tap jump. You can see a huge model change. Same thing if I were to crouch or dash, especially if I dash as part of a dash dance, because then there is this flash of the information in the form of the character standing up for one frame, which means I'm changing directions. Overall, in-game mechanics that only change linearly to analog values aren't as critical to communicate about as things that cause an animation change, from both a visual and gameplay perspective. Following this line of reasoning, passing the analog threshold for these things, so shielding, dashing, crouching, and tab jumping, should trigger sending an update. So, if you look at the green number at the bottom, the left one, that's the analog value on my left trigger, and the minimum value for shielding is 0.307. So what I mean in practice is that when we cross the 0.307 threshold, we'll send an update containing the current controller state, which, among other things, contains this reading. And for any other analog variation for that trigger, we won't. Otherwise, for a single full trigger press, we would be sending many updates. So with this in mind, here's the list of triggers that I'm going with for V1. As I said, light field threshold for analog triggers in both directions, getting out of the dead zone for the control or the C-stick, which causes a few things for the control stick and aerials for the C-stick. For the control stick, passing the thresholds for dashing right, dashing left, tab jumping and crouching. For the C-stick, passing all smash thresholds. And then, there's all digital presses and releases with the exception of A, B and start, since we very rarely care about when these button releases happen. And that's almost the list. Even though it catches most things, it doesn't catch everything. Like for example, when you're dashing, the tab jump threshold lowers by 0.1. So it's possible to tab jump from a dash without passing the threshold that we look at to catch tab jumps. So then you could say, we should add another trigger on passing the threshold upwards. Okay, but do we really want to send all 3 messages because of one full up input? Maybe not. So we could add a trigger that's conditional to the x-axis. Like, if the stick is near the edge, basically if you're rolling it upwards from the side, you may be in a dash, and this would mean a tab jump. So yeah, okay, then it should count. And there are other cases like this. If you know anything about GameCube controller modding, then you know the shield drop threshold is not -0.7, it's -0.66, which means this wouldn't properly catch shield drops either. But we wouldn't want to trigger on both -0.7 and -0.66 all the time. So we could check if you may be in shield, based on whether L or Z are pressed on the analog LR values, and if you may be, then we start checking the shield drop threshold. My point being, it's not trivial to judge which analog threshold traversals should be deemed important without being cognizant of game state. The 2 examples I gave are included, but that's it, and there surely are other corner cases, some of which I will hopefully handle in future updates. I also want to emphasize that this means that we are not sending all of the useful information. Now we're sending the vast majority of it, probably 95% at least, but it's not 100%. So when I have to shortly summarize the benefits of this, I'll probably say something like, with this enhancement, playing at this ping should feel like playing at that ping before, and what I will mean by that is that the average rollback lenses match. But saying this implies that the effect can be substituted for ping reduction, like it's the same currency. But ping reduction affects everything, so to speak, even the corner cases that this doesn't catch. So that statement on being equivalent to ping reduction is not technically correct, and I felt that, at least here, I should mention it. So, speaking of cost and benefits, you may have noticed that this problem is somewhat reminiscent of that of counting inputs per minute. Because if some analog threshold traversal is important to the game, then that sounds like something that you do on purpose, which probably means that it should count as an input. But since which analog threshold we care about is conditional to an in-game state that we can't or can't yet know about, we have to settle for estimates. For IPMs, you want to count 1 input per intentful movement, so you pick 1 threshold and call it a day. Here, we want to react to traversing every threshold that may matter, so we pick several. But I do think that comparing to IPMs gives a sane estimation of the number of extra messages sent. The Slippi IPM way is counting crossing dead zone boundaries 2 ways, except getting back to center. It's basically modeling the analog stick as an arcade stick, and doing standard counting from there. Relatively to this, I estimate the number of updates triggered to be once to twice the number of inputs according to Slippi. The average Melee Pro is at about 10 inputs per second per Slippi matrix, which translates to 10 to 20 extra messages per second compared to normal Slippi operation, unless the worse the player. It's not a lot considering that currently, Slippi uses 120 messages per second, with 1 pad message and 1 acknowledgement per frame. So that's about a 10 to 15% increase at most in the number of messages sent, which is what matters since as we only send controller data, throughput is mostly irrelevant. But since we lack proper benchmarking data as to what the added cost affects, I'd rather be conservative. Now, regarding benefits. Again, I'm only talking about the changes that the trigger system catches. As I explained earlier, with traditional rollback, if the inputs for a frame arrive just after the game engine runs for that frame, that's too bad, you'll experience a full frame of rollback. It's like the game engine is a boss line, and if you barely miss the boss, you have to wait for the next boss. So if you have a 70 millisecond ping, which means a 35 millisecond transmission time, and the delay is 2 frame lengths, which is what I assume in this graph, you barely miss the boss, and so you experience a full frame of rollback. With subframe rollback, as I showed earlier, the average rollback length that you experience is transmission time minus delay. If you barely miss the boss, that means that the important changes almost up until now would have arrived in time, so you'd roll back almost nothing. Does that mean that, in practice, if you have 99 millisecond ping with your friend, this is useless, but if you have 101 millisecond ping with your friend, this is amazing? No, it's not that discontinuous. Aside from the fact that we've been assuming that the transmission time is perfectly stable, which it is not, there is a bigger problem in that players may be ahead of each other with regard to the game advancement. You see, every now and then, your PC won't manage to build the next frame in time. It happens even to the best setups. That's just life on an operating system. When that happens, we witness the following. Because the -3 frame was lengthened, the time at which they build the second frames now differs from the time at which we build them. There is difference of game advancement between the two players. In fact, there was never a reason for the two game engines to be synced to begin with, so there's always difference, which may fluctuate with time. And if that difference is large enough, it will asymmetrically cause rollbacks, as it does in this example. Here, there's almost half a frame behind us. Because of this, even though the delay is more than the transmission time, because they start building their frames late compared to us, they also send the information for this frame later, which causes us not to receive it in time to build our frames. And so we have to roll back. Conversely, we could have the transmission time be slightly more than the delay, and they wouldn't need rollback if they're behind enough. So earlier, when I was talking about rollback length as a function of transmission time, I really meant the transmission time plus the game advancement difference. Now you may be wondering, how ahead or late can one get? Because if you're significantly behind your opponent, Slippi is going to do something about it. Because the player that's behind has an advantage, and it's not right for a player to be favored in such a way. So if we take such a scenario, where we are more than 60% of a frame ahead of them, eventually, this will happen. Slippi will make you stall for 1 frame. For 1 frame, the game doesn't advance. And now you're less ahead. In fact, you're behind them if you were ahead of them by less than a frame length, and the inputs arrive in time again. With the current version of Slippi, this can happen up to twice per second. It's not right for a player to roll back much more than the other, so it tries to keep players within half a frame length of each other. You can be momentarily outside that range, but it won't last. So with this in mind, for the purpose of our benefits calculation, a decent modelization for the game advancement offset is uniformly random between minus and plus half a frame length. And that means that the real experience rollback length graph is closer to this. You take the dashed lines, that's how it would be if both games were always in sync. And then, you take the average over 1 frame length of transmission time, and you get this. This is, in practice, how much rollback you're projected to experience depending on the ping. At 50 milliseconds, there is no improvement because there's nothing to improve. At 83 milliseconds, the improvement caps because at that point, both players are always running back 1 frame. In between, it progressively makes more of a difference. Halfway through, it already makes 75% of the maximum difference. That's assuming that you play on delay 2. If you're on 3 frame lengths of delay, it's the same thing, shifted to the right. Hopefully, this makes it understandable why I may say that at 100 milliseconds of ping, this reduces experience rollbacks by 16.7 milliseconds worth of ping on delay 2, but by 12.5 milliseconds worth of ping on delay 3. It makes sense when you consider that on delay 2, both players are rolling back all the time, whereas on delay 3, it's only 1 at a time. Well, in our cute theoretical model at least. Okay, so there's one last thing that I should mention about benefits, and it has to do with the reduced timing dispersion developments, which are my previous work and are controlled by this checkbox in the Slippi configuration. So what these do definitely deserves their own talk, so I'm not going to go too in depth here. Basically, by default, we're not properly using controller states that happened one frame length apart when building consecutive frames. The main reason having to do with running on an operating system. But there are others, and so this can interfere with frame-perfect techniques, because it can cause inputs to be misinterpreted. Like, you could do an input that should be processed as frame-perfect relatively to the other input, but because of these issues, turns out it has a 4 to 5% chance of being misinterpreted, and we attempt to reduce that by constructing the history of what must have happened on the controller's end, and cherry-picking in the near past what controller states we want to pass to the game engine, so that we make it use inputs that follow a properly periodic pace. And that's expected to slightly help with reducing input misinterpretations, as the graphs on display show. It's not that important. What's important here is its cost. Specifically, the cost of not necessarily passing the latest thing we know of to the game engine when it asks for inputs. And doing anything but always using the latest on input is going to be laggier than always using the latest on input. That just makes sense, right? So it adds lag. For the majority of people, it adds 1.6 milliseconds, which is approximately 1/10 of a frame length of input lag, which isn't a lot. The benefits aren't a lot either. But here's the thing. If you're using inputs that are slightly in the past on purpose, that means that you could send them earlier. The artificial delay you're adding, it doesn't have to be a dry loss. If you send these inputs as soon as you learned of them, they would depart early, and in that sense contribute to the delay buffer. And that's when we run into the problem that softwares aren't indivisible sentient entities. They're broken down to small parts, that are broken down into smaller parts, each with their responsibilities, their boundaries, and they have to be small enough so people can fully understand one part, otherwise development goes to shit. That's called software architecture. And in our case, the existing Slippi mechanism for controller state transmissions is driven by the game engine, which makes sense since we only send the inputs that are used by the game engine. But that means that inputs slightly old passed to the game engine won't depart earlier than if we had passed the latest inputs. In that case, not passing the latest controller state to the engine causes a dry loss of input lag. With the architectural modification supporting this new thing of sending controller states for prediction's sake, this separate stream of network messages is driven from whatever communicates with the GameCube controller adapter, and is triggered by the acquisition of new information over USB, which, by the way, is fairly unnatural. But when you do that, the departure of inputs is no longer concerned with the artificial delay that lives in between whatever pulls the adapter on the game engine, so we're not incurring it. To give a concrete example, if the transmission time is very slightly longer than the two frame lengths of delay, and the two players are in sync, the definitive input departing will barely miss the deadline for frame n. But any major state change contributing to the definitive input would trigger a message that would arrive in time. Here I've represented the artificial delay. What we really send on frame n-2 is the content of n-2.1. Well, any major update that contributes to frame n, such as this bpress, because it has to happen before n-2.1, will arrive in time to be incorporated in frame n the first time they build it. So again, we're going back to this. If we pretend that we catch everything that matters, this is logically equivalent to a 2.1 frame lengths delay. That's what I mean when I say that now it contributes to the delay instead of being an increase in input lag with no delay increase in return. With this in mind, the updated ping to average rollback length function is this. Because relatively to using the timing dispersion reduction option on the vanilla build, which is advised, it adds 0.1 frame length to the delay buffer and doesn't change input lag. And relatively to not using it, well, it forces you to use it because this implementation of Subframe rollback is built upon it. So you get the input stability benefits, you get 0.1 frame length of input lag and of delay, which is fine, since if a good PC setup was supposed to be 2 frames faster than console plus CRT before I brought up adapter overclocking, which saves 0.2 of a frame, then we can spend these on the network buffer and still match console plus CRT. Okay, so in conclusion we get this graph, which assumes the reduced timing dispersion option was on. At 50 milliseconds of ping, the development is virtually useless. Then the rollback length reduction effect increases, capping when we reach a ping of 87 milliseconds. At this point, it's projected to reduce the average rollback length by 20 milliseconds worth of ping. Like, if you're playing on delay 2 at an 87 millisecond ping, it should feel like a 67 millisecond ping without this development. As it stands, I think East Coast to France is 90-ish ping, East Coast to Sweden is like 100-ish, and East Coast to West Coast is close to these pings too, maybe slightly lower. So yeah, we should now be within one frame of rollback of cross-USA or intercontinental netplay at the same visual latencies and console plus CRT. And with that said, I think we are pretty much done. I'd just like to take a moment to keep it real. This is nice development, but it's not nearly as impressive as the fact that we even have rollback netcode to begin with. Like, it's fairly complex, it took a bunch of work on architectural hacks, enough that it warrants a separate public release for testing purposes, but it doesn't nearly compare to building rollback netcode and having to deal with RNG desyncs, sound effects, safe state issues, you name it. All of this stuff was already there. This development mostly ends at passing the prediction to the game engine. In fact, I barely had to write any assembly injection. There was decoupling the prediction from the last known input, and that's it. So yeah, let's be intellectually honest. This is but one improvement to one aspect of the huge endeavor that is rollback netcode for GameCube game. And with this said, I'm done for real. For the download and other practical information, check the description. I've tried to keep this video mostly an explanation of the concepts rather than information specific to this release, in hope of making it enjoyable for people interested in how this works and not only melee players. So I hope this was interesting, despite it probably being exceedingly clear that this is the first time I make an explanation video. If you have any question, I'm not hard to find, and if you are a melee player, then I hope you enjoy the build.